Yay! And we're back live. Oh, what a difference a couple days make. It's once again very weird speaking to an empty classroom as people are beginning to file in. As I mentioned in the post on Google Classroom, if they're for some reason, and this is the really weird thing, they're requiring me to take attendance for those students who are typically not virtual classroom. Like in my Genesis, they have people labeled as like V for virtual classroom or like something else for 5 days a week. And they're requiring me to take attendance for those people who are 5 days a week. But if you're virtual classroom, then you're just marked virtual classroom. And I don't get it. It's just weird. I don't like it. But that's why I kind of do have to take an attendance for some reason, which is just weird. So I'm not going to ask just yet. I'm going to give it a couple of minutes because people are still filing in. And of course, this video is going to be saved, so I will be able to go back and see the live chat, and I'll be able to take my attendance later today. But I'll just make sure that, of course, you're signed into your school email and not that it's going to be like some weird personal YouTube account. But if you could leave a comment in the chat indicating that you are here, and as long as your name pops up as your actual name, then I'm going to say, hey, that's that person, So leave your comments in the live chat and I can see the names popping up right there. That's fantastic. I appreciate that, guys. Thank you. And like I said, I'll be able to go back and look at this video since it will be saved. And sorry, time to learn. I'll be able to look back at this video and I'll be able to see exactly the names that are popping up on this thing right here. So yes, our school district has finally taken the, I'm going to use my words very carefully here, the reactive step instead of the proactive step of shutting it down for 2 weeks. But here I am, and would you expect nothing less but me in a shirt and tie? I don't know. I see other teachers walking in, they're just wearing like shorts and polos and whatnot. No, why would they wear shorts? No, I'm tired. Oh, goodness. Anyway, like I said, I'm stalling because I'm giving people a couple of minutes to get in. Normally, I don't go live until about 7:24, which is why I wanted to give people a couple of minutes just to kind of get settled in. And of course, if you haven't already left a comment in the chat indicating your attendance of this live stream, that would be appreciated. And of course, if you do have any questions, this is going to be weird inception, but I do have the live chat on my phone right there that I can look at that inception. Oh, my word. But I'm going to be able to look at that so I can see your comments. That is such a weird inception. I love it so much. Anyway, I'm going to get started then. Just a couple of reminders. This is part of my getting started type deal. Number one, I'm looking at my calendar and you can't see my calendar, but you have 2 weeks until midterms. I am going to be reviewing for a couple of those class periods beforehand. So this should be the last week of instruction before midterms. And then next week we'll be reviewing for midterms. Next, I posted that video as promised, reviewing those homework questions. Make sure that if you get the opportunity to look at that, you do. I believe I put the comment in oh, no, I didn't. Oh, no, I didn't. Why didn't I do that? Yes, I did. Yeah, I posted the assignment saying, hey, watch this video. Yes, that's what that assignment was. Excellent. So I did make that video for you guys to review those homework problems on probability. Finally, before I actually get started, because I'm remembering all of these things in my head, I am going to be throwing out a brief assessment on probability before I leave the building here today. I said it was going to be early this week, and I want to do that. So I am going to be posting an assessment in the beginning, or before I leave here today at some point, for you guys to knock out for me in regards to probability. It's been a weekend. We had an emergency faculty meeting on Saturday morning. Goodness. Sorry, it's just I don't know what's going on anymore. Anyway, I'm gonna get started. So, if you do not already have them out, I'm gonna need those notebooks out and open. Of course, you probably already do, so good for you. Anyway, I'm gonna flip my camera over so you can see exactly what I am working on. Chapow. Again, if this were my setup at home, my goodness, would I have a much better setup than this. But whatever, them's the breaks. Okay, there are two main things that I want to do today. One of them is I want to wrap up a little bit with combining random variables, finding expected value and whatnot. I want to finish that up with you today. And then I want to introduce geometric and binomial distributions. Probably just binomial today. It depends on how much time I have. But we'll figure this junk out together. Now, your textbook actually does have a really amazing example in the random variable chapter. It has an amazing example in regards to random variables that I want to give you the kind of the Cliff Notes version of it today. So today is the 11th. There we go. And I'll try to do my best to avoid the glare in the middle. I know I do apologize for that wonderful glare that we have. And this is just going to be random variables continued. Random variables continued. Fun facts. Anyway. Hooah. So in your textbook, they actually do have this amazing example of a restaurant called the Quiet Nook. And the Quiet Nook offers what they call the Lucky Lovers Special. Yes. Now, typically in years past, mind you, I would get to this example sometime around Valentine's Day. But in recent years, I've had to speed up my timetable of AP Stat, and thus you get this in the middle of January instead of the middle of February. But that's where we're at. Now, the Lucky Lovers Special works like this. At the end of your meal, no matter what you ordered, at the end of your meal, the waiter brings out to you 4 aces, and you have to randomly select an ace. And if you end up selecting a black ace, then you get a $0 discount. Move that up just a tiny bit again, hopefully avoiding that glare. But you get a $0 discount. Oh well, sucks to be you. Pay the full amount. If you get the ace of hearts, however, you get a $20 discount. You get a $20 discount. Good for you. You get to impress the lady. I don't know. I'm upholding stereotypes right now. Now, if you get the ace of diamonds, however, you get to try again. Try again. And if you get the ace of hearts, you get a $10 discount. I'm going to recap that in a moment just because we need all of that information in order to create the probability distribution. So Lucky Lover Special, you go out for a dinner. At the end of the meal, the couple, I should say, the waiter brings the couple 4 aces. If you select a black ace, no discount. Sucks to be you, pay the full amount. If you pull the ace of hearts, you get a $20 discount. Good for you. If you pull the ace of diamonds, you get to try again, this time without the ace of diamonds. And if on the second try, you pick out the ace of hearts, you get a $10 discount. Awesome. Let's try to set this thing up. Now, in terms of random variables, I'm going to set up my little table right here. There's multiple ways to set up this table, but I'm going to set it up this way. Let's set it up X for the discount, and let's set it up probability of X like that. Yeah, I'm going to set it up just like that. Now, again, X, which is the random event that is happening, has to have a numerical value attached to it. And we do have that in the dollar discounts. See, either you're going to get a $20 discount, a $10 discount, or a no dollar discount. Oh, you can't see the no dollar. There we go. Could be any one of those. But not all events are created equal. In fact, you get the $20 discount if you pull the ace of hearts. Thus, you have a 1 in 4 chance of getting that discount. Cool, fantastic. What about the $10 discount? Now I'm going to verbalize this. To get the $10 discount, you have to first pull the ace of diamonds, which is a 1 in 4 chance. And then you have to pull the ace of hearts, which is now a 1 in 3 chance. Let me repeat that. In order to get the $10 discount, you have to pull the ace of diamonds, which I'm going to do a little scratch work off to the side here, which is a 1 in 4 chance. And then you have to select the ace of hearts, which is a 1 in 3 chance. And notice what I did right there. I multiplied them, or I should multiply them, meaning that there is a 1 in 12 chance of getting the $10 discount. You have a 1 in 4 chance of getting the $20 discount. You have a 1 in 12 chance of getting the $10 discount. Now we have to figure out the $0 discount. Now, there's 2 ways to get the $0 discount. You could actually figure out the 2 events in question, meaning you pull the black ace first, or you pull the black ace on the try again. There's 2 scenarios where that happens. And you could, conceivably figure that junk out. Or, bring up my calculator here. You could do something like this. I'll hit enter in a moment. Again, the general idea being that all 3 events, these are the only possible outcomes that there are, so altogether should be 100%, meaning if I want to find the $0 discount, I'm going to have to take the complement, 100% minus those 2. Chapow! 2/3. Like I said, there is another way of figuring that junk out, but that's probably what I just did is the easiest way of doing that. So, expected value. Now, expected value, I'm just going to easily done by hand here, if you had to. Expected value, if I had to multiply these 2 together, I could do this. That's a 5. And then 10 times 1/12. What is that? It's the fraction 10 over 12, which reduces to 5 over 6. I'm just going to put 5 over 6 here. And that's 0 when you multiply the 2 of them together. And then I would just add this column up. Find the sum of that column. Bring that up right there. There we go. If I were to find the sum of that column, well, 5 and 5/6, clearly. But 5/6 as a decimal, it rounds. expected value of the discount is approximately $5.83. Now, like I've said in the past, standard deviation, a bit of a pain to have to calculate by hand. So I am going to utilize my graphing calculator, which you obviously do have on your computers, which is wonderful. Let's clear that. Stat, edit. Oh, I got to clear that junk out. That was for a different class. Cleared, stat, edit. Good. 20, 10, 0, 1/4, 1/12, 2/3. Good. If you enter in all of that data into your L1 and L2, as we've learned the hard way, if you hit stat, go over to calc, 1var stat, you would have to change the frequency list to say L2, which there's a couple different ways to do it, but the easiest way is just hitting second and then the number 2. If you calculate, it will spit out the expected value, as we already know, but it will also spit out the standard deviation, which is what we need for later problems. I'm going to write this down right here. There we go. So the expected value of X is approximately $5.83. The standard deviation of X is approximately $8.62. Now that should make sense because this thing is deviating as low as $0, which the majority of people get. The majority of people are going to get no discount. But then a few are going to get the $20 discount, and even fewer are going to get the $10 discount. On average, about $8.62. Deviating from the mean. Crazy. So this is where this problem gets a bit more in-depth. Because in your textbook, they take this lucky lover special and they expand upon it using different scenarios. Let me show you what I mean. In one scenario, they say, okay, a week before, Valentine's Day or whatever, there were these $5 discounts or $5 coupons, I should say coupons, that you could add on after this whole lucky lover special thing. And they wanted to know, okay, well, if people are coming in with $5 coupons, what is the new expected value and the new standard deviation? Well, let's take a look. So currently, the expected value is 583, and the standard deviation is 862. But now we have $5 coupons. So what happens to them? Well, the expected value of X plus a $5 coupon. Well, this isn't a random variable, but it's like, well, what do I do with this whole $5 coupon thing? Some people have written it like this, where they put the 5 on the inside. I'm like, okay, that technically does work. If you want to put the $5 on the inside, and then it's just what, $10.83? And I'm like, yeah, it's just $10.83. Cool. What about the standard deviation? Now, the standard deviation, as I've made a huge deal about last Thursday, when you are multiplying, dividing, adding, subtracting the same value to every data point in the standard deviation, adding and subtracting does not affect the standard deviation. It doesn't. In fact, if you try to do something like this to the standard deviation, nothing would happen to it. By definition, it would remain exactly the same. if you try to add or subtract the same value to each data point, and the data points in this question are people coming into the restaurant with the $5 coupon. It's like, oh, I got this discount. Okay, plus $5. I got on the discount, I should say. I got this discount plus an additional 5 off. I got this discount plus an additional 5 off. Every data point has $5 being added to their discount, thus everything being shifted over. The standard deviation doesn't change. That's what happens. Whereas, let's just say you have two couples dining together. If you have two couples dining together, now this is a different scenario. The restaurant offers double discount. This is just an extra scenario. Now, the restaurant does offer those $5 coupons, and if they do, then on average, you would expect $10.83 as a discount, but the standard deviation does not change because everything just shifts over. The $0 discount would have become 5, the 10 would have become 15, the 20 would have become 25. Everything shifts over, but the standard deviation remains the same. The spread remains the same. The variation remains the same. However, if now you have two couples dining together, discount double check. If that happens, now you have a scenario. Yes, the expected value of the discount is now doubled to give you $11.66. And because standard deviation is affected by that doubled or that multiplication division operation, now the standard deviation is affected by that multiplication. If you think about it again, the $0, $10, $20 discounts doubled would be, well, 0 and 20 and 40. Everything is a bit more spread out. And as a result, the standard deviation doubles. That's typically what happens with this stuff. Addition, subtraction of the same value to each data point, addition, subtraction of the same value to each data point does not change the standard deviation, but multiplication, division of the same data point does. Crazy. Now I'm really going to mess with your heads. Let's keep thinking about these two couples dining together. Double date. They have this double date, thus they get the double discount. But they only get the double discount if they pay on one check, meaning they are dining together. What if they dine separately? If they dine separately, they don't get the double discount. If they dine separately and they get separate checks, the waiter will bring over 4 aces for one couple, and they'll do the whole thing. And the waiter will bring the 4 aces over to the other couple, and they'll do it again. So these two couples, they decide, okay, let's try to pool our discounts. Let's get separate checks so we each get a shot at the $20 discount. Because, hey, if we each get the $20 discount, that would be awesome. I mean, that would be cool. But let's just see what happens. Will it affect expected value and standard deviation? That's the big question. So here's the scenario. You have two couples, but now they're getting separate checks, which means they each get a shot at it. Unsurprisingly, if you had these two couples each attempting, and look at this down here, I did X sub 1 and X sub 2. If you had these two couples dining separately, yeah, I can add the two expected values together, 583 plus 583, to get 1166. Oh, it's the exact same expected value. Yes, no big deal there. But what happens to the standard deviation? Because now with the standard deviation, it's no longer I'm doubling it. I'm not doubling it. I'm combining two independent standard deviations. I'm not doubling a single standard deviation. I am trying to add together two independent events. This is why I made such a big deal about independence last week. If I try to add these two independent standard deviations together, I am not allowed to. I'm not allowed to. I cannot just combine two independent standard deviations by adding them together. No. I have to convert them to variance first. And if I convert them to variance, this would be 8.62 squared. If I square it, it becomes variance, plus 8.62 squared. They get squared first, then they get added together, and then they get square rooted back into standard deviation. This is the proper procedure. And one might think, well, you're going to get the same standard deviation. No, you're not. You're not. If you actually did this correctly, let me show you. Hold on. Clear. 8.62 squared plus 8.62 squared, and then a square root. That answer to get $12.19. Chapow. What happens is this. If those two couples are dining together and they get one check, and the restaurant's like, hold on, now they're interrupting me.
Good morning. Please excuse the interruption. Could any paraprofessionals or any other staff who does not have a course load, will not be meeting with students and doesn't know what to do, please stop down to the main.
I don't know if you all can hear that announcement. They just interrupted me with an announcement, and now I'm mad at them. I want to throw something. Back to this. Okay. If those two couples are dining together and they get one check, they get the same exact expected value, 1166, but if they're dining together, their standard deviation is over $17. But if they get separate checks, two independent events, there actually ends up being less variation based on the way that the standard deviations are combined. There's a key thing here. There's a key distinction between these two separate events. Yes, these two events right here, let me move this up a bit. Here we go. These two events right here get the same expected value. Right here, this is when the two couples were dining together. Double discount on one check. Yeah, same expected value. And the standard deviation would just be doubled as a result. But when you have these two independent events, all of a sudden, there's less variation. Now, there's a reason for that. And I want to talk about that by upping the number of couples. I want to up the number of couples. Let's say you do this ridiculous thing with your friends where you go to this restaurant, the Quiet Nook, and let's say that there are 40 couples dining together. I could spell together today. 40 couples. I cannot say that I've actually done this. One time I went, that's a long story short, I went camping with a bunch of friends and we were packing up on a Sunday and it started raining while we were packing up and we didn't get to make breakfast because it started downpouring and we had to like pack everything up. So we got in the cars and we drove to the Red Lion Diner on Route 70. At one of those circles, went to the Red Lion Diner and I walked in by myself at first and I'm like soaking wet. And the guy's just like, can I, how many? And I'm like, there's like 20 of us. And then he's like, and I'm like, yeah, and then they all walked in behind me. It was hilarious. But imagine 40 couples dining together, 80 people. Now there's two scenarios. One in which the diner doesn't really offer it, and one in which they most likely do. The one that they probably won't offer is this. The one they won't offer is 40 times the discount. They probably won't offer 40 times the discount. But they could, they probably would offer 40 separate checks. Now, if you think about it, with the 40 separate checks, you got a bunch of people. Mind you, they're going to pool all their money together, but a bunch of people getting like $20 and $10 and $0 and everything in between. Well, there's nothing in between. Or 40 times the discount, meaning you could get a $0 discount or a $400 discount or an $800 discount. In this scenario right here, 40 times the discount, there's only three particular numbers that would show up for all of, for all data points. 800, 400, or 0. Whereas with 40 separate checks, it's a combination of a bunch of zeros, 10s, and 20s, but you don't know exactly how many there are. There's a lot more numbers in between. Maybe they'll all get $20 discounts. Maybe half of them will get $20 and half of them will get $10. Maybe all of them will get 0. I don't know. But because of the 40 separate checks, there's more numbers in between the 800, the 400, and the 0. And as a result, there should be less variation. But let's actually do the calculation here. If I'm going to do the standard deviation of 40 times the discount, I actually didn't write this down. I'll do this separately right here. $8.62, 40. Whoa, standard deviation, $344.80. 40 times the discount. But if I'm doing 40 separate checks, I'm not going to write this out, but it would be like 8.62 squared plus 8.62 squared plus ... 8.62 squared 40 times, and then I would have to square root it. Well, let me go. I'm going to go to the. No, I'll do it here. Hopefully you can see that. I'm going to zoom in a little bit. It's going to be weird. 8.62 squared, but then I'd have to do that 40 times, so times 40. And then I would have to square root that. All of a sudden, the standard deviation is $54.52. If you're doing 40 times the discount, which the restaurant probably won't offer, there's much more variation because, again, you're either getting 800, 400, or 0. It's all spread out. Whereas 40 separate checks, most likely those numbers are going to be a bit closer together. A bit closer together. I love this stuff. Okay. Now, with the time that we have left, because we do have plenty of time, and I know how much you miss school and my glowing face, but I wanted to introduce to you the idea of a binomial distribution. Now, you may have heard of binomials in algebra class, binomial expansion, where you take something like x plus 1 and you raise it to the third power, and then you get to multiply x plus 1 times x plus 1 times x plus 1. There is a connection. I'm not going to really talk about that, but there is a connection between the algebraic binomial expansion and the binomial probability distribution that I'm going to introduce to you today. There is a key connection between them, but that's not the point. The point is this. So let me introduce to you the idea of a Bernoulli trial. Bernoulli is actually a famous mathematic family back in the 1600s. Depending on who you're talking about, it could be, I think they were either brothers or cousins or like uncle and nephew. I don't know, whatever. But it was a family. A Bernoulli trial has an outcome of either a success or a failure. When it comes to probability, obviously we know it's a bit more nuanced than that. It's a way more nuanced than success or failure. But if we look at an event as either resulting in a success or a failure, then we can determine a lot more stuff. Now, just for the sake of argument, let P be the probability of success, and let Q be the probability of failure. You're going to see P and Q in this chapter a lot. P is going to be known as the probability of a success, and Q is going to be known as the probability of a failure. Now, there are a bunch of formulas that I could potentially introduce to you. I'm debating about which one I really should do first. Okay, fine. I'll start with the geometric one. I was hoping to get to the binomial one today, but I guess I'm going to have to save the binomial one for next time. It just makes more logical sense to go with the geometric one first. Okay. Let's talk about a geometric distribution. There are two particular models that we're going to be talking about that involve Bernoulli trials. Again, Bernoulli trials being success and failure. One of them is called a geometric model. Now, in a geometric model, you are looking to get a first success. You are looking to get a first success, which I'm going to put in parentheses here. Getting a first success, typically in an unknown number of trials. Now, obviously, there are sometimes situations in which you would have a finite number of trials. Like, for example, students at Barnegat. There's 1,000 students at Barnegat. Okay, cool. I'm looking for the probability geometric model of getting a first success of like someone being, I don't know, like red hair and left-handed or some junk like that. I don't know. Red hair and left-handed. There is a possibility that I would get through all students of Barnegat High School and none of them would be, red-haired and left-handed. None of them. And if that's the case, it's like, oh, crap, I didn't get my first success. But I'm still describing a geometric model. A geometric model is describing the probability of getting your first success within a certain number of trials. But you don't know how many trials you may end up having to go through. Theoretically speaking, if I took a penny and I said, I'm going to keep flipping this penny until I get a tails. Theoretically, I could be sitting here for a very long time. It's not a guarantee. I mean, theoretically, I should be getting it. I should be getting that first success within a certain amount of time, but we'll see what happens. Now, I've already mentioned what P and Q are. They will have P, which is, again, the probability of success, and Q, which is the probability of failure. But then they will also have X, which is the number of trials until your first success. It's the number of trials until you get that first success. And at this point, it's just like, I'm just throwing a bunch of words at you. You don't really know exactly what we're doing with it just yet, but you will in a few moments. For example, let's say that I had a die, like this one right here. There we go. Now, this isn't your normal die. This die is not 1 to 6, unfortunately. It's 0 to 5 for some reason. There's 0, 4, 3, etc. But let's just say I'm going to roll this die, and I'm trying to find, okay, what is the probability that I would roll a 3 within 10 rolls or something like that? Let's say I'm going to roll it 10 times, but let's just say I word it exactly like that. What is the probability that I will roll a 3 within the first 10 rolls? We can calculate that. There is a way to calculate that. Now, let me specify something different, though. What is the probability that I get that first 3 on the 10th roll? If I roll it 10 times, there's a 0. I got a 3. Let's just pretend I didn't get that. There's a 5. I got a 4. I got a 0. I got a 2. I got a 4. What is the probability that I would get that first success on the 10th trial? Now, I'm going to show you multiple ways of doing this, but here's what you have to assume. First and foremost, each trial is technically independent of the next. Each trial is independent of the next. The probability doesn't change from one trial to the next. Every time I roll the die, I have a 1 in 6 chance of rolling a 3, which means I have a 5 in 6 chance of not rolling a 3. You see, if I were going to actually calculate this out, 4, 5, 6, 7, 8, 9. There are 9 fractions 5 out of 6. Because if I'm going to say, okay, what are the chances that I would get a 3 on my 10th roll, implies that I failed to do so in my first 9. I failed to roll that 3 in the first 9 trials. And then finally, on the 10th trial, I got it. And there's that number right there. Oh, that's painful. Not painful, but just tedious. Ugh. If only there was an easier way. There is an easier way. I'm going to show you the easier way. But first, let's write down some formulas. So in a geometric model, the probability of success on trial X. Success on trial X. Zooming in, zooming in, zooming in. A little more. There we go. Success on trial X indicates the following calculation. Q being the probability of failure raised to the x minus 1 power, which makes sense with what I just did, because if we were doing trial 10, I did the probability of failure 9 times. It would be Q raised to the 9th power in that example. And then finally times the probability of success. Cool. Phenomenal. Oh, fantastic. I wonder, if I was rolling that die, how many rolls would I expect to have to do in order to get that first success? How many rolls would I expect to have to do in order to get that first success? I mean, logically, you could figure it out because it's, a die. There's only 6 sides to it. Just for the sake of argument, the expected value, the expected trial that you would have to wait to go to in order to get that first success would be nothing more than 1 divided by P. In this instance, you take the probability of success, you take 1 divided by that, and whatever pops up, that's the number of trials that you would expect to have to go through. Expected number of trials to get first success. That's the expected number of trials to get that first success. I can't see it. I wrote a mu there. I'll move that up. There we go. There is a standard deviation as well. And I'm going to write down this formula, but I'm just going to warn you flat out that the formula that I'm about to write down, I have never really seen people ever use it in AP. I've never seen people really use this formula in AP, other than like a problem in the textbook that randomly asks for it. It's kind of dumb. But there it is. It's the square root of Q divided by P squared. Again, it's kind of dumb. Personally, I think it's kind of dumb. No one ever really uses it. But they do have it in the textbook. And then, heaven forbid, they throw the one problem at you. Well, there it is. The expected standard deviation. Now, using all of these formulas, if only there was an easier way. Well, there is. Let me show you something on the calculator. I have this calculation right here. There it is. It just focused. Oh, no, it went away. There it is. It just focused. If I'm going to roll a 3 and I'm going to get that first success on the 10th try, it's about a 3.2% chance. Okay. You can't hear what I'm saying. You did not go deaf. I'm simply typing something into the calculator and getting the exact same number. I like that better. What the heck did I just do? What I just did was I utilized the geometric probability distribution in my graphing calculator in order to do that exact same calculation. And it does it for me. Let me show you where it is. Go to your graphing calculators. If you go to your graphing calculator and you hit second vars, it'll bring you to this function, not function, but like the area in the calculator known as distributions. And we've been here before. We've been here for normal CDF. But now, if you scroll down to the bottom, you could also just hit up once. But if you scroll down to the bottom, now all of a sudden you have a couple geometric distributions. You have a geomet PDF and you have a geomet CDF. Yes, you also have binomials as well. And yes, we will be using those binomials next time. Today, I want to stick with the geometric. There are two of them. There's a PDF and there's a CDF. The C in CDF, I want you to think of it as cumulative. And I'm going to show you something a little bit that's going to hopefully distinguish between PDF and CDF, but that's not what we need right now. I'm going to the PDF. Geomet PDF. Oh, look at that. Probability of success. The trial I want to get that success on. Paste. Enter. There it is. I want to be very clear about something. Using the calculator to get that answer will not always be your saving grace. I'll zoom back out. Hold on. Knowing how to do this formula will be your saving grace on geometric problems. I do have another formula for binomial, but again, that's next time. But knowing how to do this formula for geometric distributions will be your saving grace, because who knows when you're going to get a multiple choice question where all 5 answers are like, hey, which one is the correct calculation? You need to know how to do this. Sometimes it's faster to know how to do it this way. Sometimes. And it makes logical sense in the idea of like, okay, well, I got to multiply. I fail the first bunch of times, and then I finally get a success. Yay. Absolutely. Yes, indeedy. Positively. I don't know how many other words I can say. Okay. Let's talk about Geomet PDF versus Geomet CDF. Geomet PDF versus Geomet CDF. The PDF is the probability of getting first success on exactly the xth trial. Let me repeat that. A Geomet PDF, and I underline the word exactly because that's the key phrase there. It's the probability of getting that first success on exactly the 10th trial. Now, a CDF is cumulative. It is the probability of getting first success on or before xth trial. It's the probability of getting it on the first success on or before the xth trial. CDF is cumulative. So for the example of the die, bring that die right there. There we go. In the example of the die, it would be getting that first success on the 10th trial or the 9th or the 8th or the 7th or the 6th or the 5th or the 4th or the 3rd or the 2nd or the 1st. It figures out all 10 probabilities and then adds them all up. Oh man, that would suck to have to do by hand. Yeah, it would. Thankfully, you have a calculator. Check this out. Second vars, Geomet CDF. 1 divided by 6 is my probability of success. 10 is the trial. Now, I'm doing CDF, so this answer would be getting that first success, rolling that 3 on or before the 10th trial. What this will calculate is basically the 10th trial, or getting it on the 10th trial plus getting it on the 9th plus getting it on the 8th, all the way down to plus getting it on the 1st. And it adds them all up, obviously. So there's about an 84% chance that you would get that first success on or before the 10th trial. I would expect, check this out, I would expect that I would get it on about the 6th trial. This geometric probability has a peak around trial 6. And then the farther you go out, it's like the less likely it's going to happen. Here, check this out. What are the chances that I get it on the first trial? I wonder, what are the chances? If I have a 1 in 6 chance of success, what are the chances that I get that success on the first trial? Oh yeah, it's 1 in 6. You can't see it, but I'm making a face right now. The way that information is typically typed in is you got to type in the probability of success first, and then the trial that you want to get that success on. Now, mind you, I'm beginning to wrap up. I'm not going to write anything else down for today, but I'm wrapping up right now. There's a couple of conditions that come into play for Bernoulli trials. Again, Bernoulli trials being the success and failure, or getting those are the only 2 outcomes. Either you succeed or you fail. Not that one is good and one is bad. It's just that one of them is what you're looking for and the other one is not. Each trial must be independent from the next. If you cannot guarantee independent trials, then I'm sorry, you do not have Bernoulli trials. And thus you can't use the geometric, or in the next class's case, the binomial. There is another condition that has to do something called the 10% condition. I'm going to talk about that next time. But it's this weird condition that actually does come back and haunt you later on in the school year. It really does. Because what I'm doing right now is I'm actually laying the groundwork for some of the things that we're going to be doing later on in the year, where certain assumptions and conditions must be met. There's a certain minimum threshold of evidence that you have to present in order to make an appropriate claim. That is what AP Stat is all about. And I go back to the beginning of the school year. AP Statistics is making confident statements with limited information. That's what it is. Okay. Let me flip back over here. I don't know why I just flipped back over there. Why did I do that? I don't know. I didn't need to do that. All I got to do is walk over here and be like, hey. Well, that's it for me. Like I said, I am going to be posting something today in regards to the probability chapters that we did prior to this. An assessment of sorts. I'm going to sign off. But you guys have a wonderful day. Go to your next class. Don't spend too much time in the hallway. Such a weird day. Oh my gosh. And there's the bell. See, I made it. Anyway, I'll see you all later.